Hello, my fine young students. We're going to work on today 2.2, Intramolecular Forces and Potential Energy. Notice we've already covered in class 2.1, 2.3, and 2.4. They went better together with ionic solids, metallic solids, so we could compare them. So we're going to go back and look at some intramolecular forces. Remember, intra means within, so we're talking about the forces that hold the molecule together, the one single molecule together. You're going to find text pages here, page 387 to 394 and 411 to 416. They can help you out a little bit, especially the diagrams. Look at the diagrams. Those are good stuff. First off, with the strength of ionic bonds, what I want to show you and refer to you, ionic bonds are very strong. So it does require lots of energy. And I want you to see here, it says very endothermic. And we briefly discussed this in class today, but notice it's endothermic and you've got a plus charge, or I'm sorry, a plus energy or positive energy for your lattice structure. Don't get freaked out by the lattice structure. All that the lattice structure is saying is, hey, you've got this ionic solid and they're all together, and basically it forms this nice, neat, orderly structure. This plus is indicating that it's endothermic, meaning that the actual molecule or the bonds will actually take in a lot of the energy instead of giving it out. If this was a minus, that would be exothermic, and that would mean that the bonds would be releasing energy. So we have to look at good old Coulomb's law again, because we love Coulomb's law. So Coulomb's law, again, we're looking at the charge, the Q's, divided by the distance squared. Sometimes that's listed as radius squared. It doesn't really matter. We're just looking at the distance between the ionic centers. So we're looking basically from nucleus to nucleus, okay? The melting point of ionic solids. Which compound from each set has the greatest melting point and why? So what we have to think about here is we have to think about Coulomb's law. So we've got the Q1, Q2 over the distance or the radius, either one squared. And so again, it's distance from nuclei to nuclei. So let's think about the internuclear distance. So if we've got lithium and fluorine, we've got a +1 and a -1. Lithium and iodine, we've got a +1 and a -1. However, iodine's much larger, so this distance from the nucleus of lithium to the nucleus of iodine is going to be bigger. Therefore, the melting point is going to be a little bit easier to melt because it's not held as tightly. So the highest melting point then is going to be lithium fluoride because it is closer, the distance is smaller, we do have a greater Coulombic attraction. If we look at MgCl2 and MgO, we've got a 2+ and we've got a minus, we've got a 2+ and a 2-. So if you look, for example, MgO and Cl is going to be in the third energy level, so therefore that distance is going to be larger. So it's going to create, the distance is actually going to kind of trump the charges. So it's going to create more internuclear distance, and the charges are going, if this distance increases, then the whole Coulombic attraction is going to decrease. So therefore, MgO is going to have more of a Coulombic attraction there. Down here with Na and F, we've got a plus and a minus, a 2+ and a minus, looking at our Q1 and Q2. But then again, we're looking at fluorine, we're looking at iodine. That iodine is making the distance very much larger. Therefore, it's NaF is going to have the greatest melting point because it's all pulled in tighter. Here's some reasoning here just to help you out if you want to take a minute and just read over these reasons again. But again, we want to relate it to Coulomb's law. Okay, now we're looking at it from a little bit different perspective. Which of the following metal fluorides would have the highest melting point and why? So metal fluorides were basically, we can throw any metal with fluoride, with fluorine. Fluorine would be our anion here. So which one's going to have the highest melting point and why? Let's take a look. We're going to have B. Now let's look at this. B would have the higher melting point because the ionic charges are +1 and -1 for both compounds. but the metal cation in B has a smaller radius. So what I want you to see here is that here is your metal cation, and it does have a smaller radius. However, with the comparisons of the two, when you have when they're closer together and they're smaller, you're basically thinking about this Coulombic attraction from one inner part of the nucleus to the other part, and that is much smaller than what you have the distance here. So therefore, you're going to have a higher Coulombic attraction over here. So B is going to have a higher melting point. On with bond energy. Let me scoot my face over a little. With bond energy, you can also see the potential energy. So this is where we're going to see that bond energy graph that we kind of looked at today. But the potential of energy of these valence electrons are going to decrease as they approach the nucleus of another atom. So therefore, once these electrons actually get close to that nucleus of another atom, they're going to have a lower potential energy, meaning that they're closer together. There's the electrostatic attractions are going to be a lot different. So the bond energy is actually the energy that's released during the formation of a bond. So that potential energy decreases as the atoms move closer together. And I'm going to show that to you on a slide here in just a minute with the internuclear distance and the energy. So let's also think here, the same amount of energy must be added in order to break that specific bond. So the binding energy that holds it together, you need basically that equal and opposite amount to actually break that specific bond. So therefore, your potential energy, as the atoms move away from one another, that potential energy is going to increase because it's going to be actually easier to break those bonds as they move easier or farther away from each other. So then the amount of energy that's required then to break the bond between two specific atoms in a molecule is the same as the amount of energy that's released. So what we need to think about here, when it's released, we've got XO. When we express the energy, it's going to be negative something kilojoules per mole. Okay. The amount of energy required to break the bond is going to be endo, because that energy is being taken in. It's going to be a plus charge kilojoules per mole, whatever like that amount would be here. So let's take a look at this in terms of bond energy a little bit. So it requires, in order to break the bonds, notice it's endothermic. Look at that plus sign. So, and the energy requires to actually break the bonds, because you have to put the energy in there. The system will absorb that energy for the bonds to break. Then that same energy is released, that same amount of energy is released when the bonds between the chlorine and hydrogen are actually formed. So notice on this side, we've got hydrogen and chlorine that form that bond. Once they form together, we're going to release the bond, or I'm sorry, release the energy. But once you break that bond, these are absorbing the energy. So they're endothermic again. So we've got to get that thing in our head about releasing and absorbing the energy, and endo and exothermic. Now, this is the chart that I showed you in class today. And it also, I'll post another video about reading bond energy graphs. But what you have here is basically your internuclear distance versus your energy. So what you want to see is, notice how closely packed these two hydrogens are and how far apart these two hydrogens are. So there's a specific sweet spot that basically creates your highest bond energy. And so you want a high bond energy because you want a decent amount of energy to hold that bond together, because therefore the binding energy to hold it together is going to be equal and opposite the energy it takes to break it apart. So your internuclear distance, this right here, is going to be 0.074 nanometers. And so that's how far apart the two nuclei are going to be. And then you're going to see that it takes negative 458 kilojoules to actually create that bond. So to create the bond, you're going to have to release energy. To break the bond, you're going to have to they actually gain the energy. Now, potential energy does decrease as attractions between the nuclei and the valence electrons pull the atoms together. So as the atom from one and the atom from other, as the nuclei get closer together, we have a potential energy decrease because there's a greater attraction here. So again, this is just explaining like what you saw on the graph before this. Now, here's another thing just to think about. As the atomic radii of bonding atoms increase, so the atomic radii, remember the distance from the nucleus to the outermost electron, as that increases, the bond length increases and the bond energy decreases. So what you have to think about here is the bond length increases. So if you have like a larger atom, for example, and it's bonded to another atom, then that as the radius gets bigger, your bond length is going to increase. Whereas if you have a smaller radius, your bond length is like, oh, you're just going from nuclei to nuclei. So actually this one's going to be stronger because the Coulombic forces are less. So you have to think a closer proximity to the shared electrons, therefore you're going to have a stronger force of attraction between those protons and bonding electrons. So when that force of attraction is greater, as in when it's smaller, it requires more energy to break the bond. So therefore, you're going to have to create that binding energy. So just real quick, bond energy versus bond length. I talked about this today just briefly with bond length. So you have, let's look at our halogens here, chlorine, bromine, and iodine. So chlorine will have the smallest radius, where iodine would have the largest. So therefore, if you have the smallest radius, your bond length correlates to also being the smallest. Iodine, when you have the largest radius, it correlates to being 0.213. So you can see the differences here. So as the atomic radii increase, bond length decreases. That makes total sense. It's like common sense. Potential energy increases and the bond energy then will decrease because it's not as difficult to hold it together. So let's take a look at this one. Consider the space-filling models below. Which molecule has the least amount of potential energy associated with this bond? So we have to look at the sizes here, and we want to tell the difference between basically the internuclear distance. So if we take a look at that, we're going to have our lowest potential energy is the shortest bond length. So we got a lower bond energy as it has the largest bond length. So we're taking the middle of here to here. We're looking at the bond length, and I'm writing in red totally. So we're going here to here. So which bond has the lowest? Which bond has the longest bond length? Bond energy and length also, like I told you before, we've got single, double, and triple. Think about the attractive forces between the three. I always tell you guys, single is like a dating relationship, can be broken. It's not super duper easy to be broken. Think of a double bond as an engagement, like it's stronger, it's a stronger bond, it still can be broken. A triple bond, think of as marriage. It takes a lot to break it, and I wish it took more, honestly. But as the electron density then between the positive nuclei increases, the attractive force between the protons and the bond electrons increase. So you have to think about this. As the electron density between the positive nuclei increases, so the electron, we get more electrons between them, the attractive forces also increase. Well, that makes perfect sense. Because you've got more electrons between them, there's going to be more attraction because those electrons are going to be going after the nucleus of the other atom. Finally, here's just a chart just to kind of like pull that together and show you a little bit more. Fluorine typically makes a single bond, oxygen double bonds, and nitrogen is notorious for making triple bonds. So you can kind of see that there and compare those bond energies and bond lengths. Bond order, whenever we refer to bond order, it's just the number of bonds between two atoms. That is terminology that we will use in the future as well. When we talk about bond order, don't get wigged out. Single bond is a bond order of 1, double is a bond order of 2, triple is a bond order of 3. Do not make that harder than what it is, for real. Because people get kind of wigged out with the idea of bond order, and they're like, what is that? Single, double, triple. That's all. Here's just a few things to look at for examples with the bond energy versus bond length. And so you're just looking to see some examples here. The carbon-carbon bond, in which molecule has the lowest potential energy. The carbon-carbon bond, in which molecule has the lowest bond energy. What you'll notice here, how many bonds do you see? 1, 2, 3. You've got a triple. Okay, you've got a bond order. A bond order of 3. This one, you've got a double. You've got a bond order of 2. Okay, so put that together with what you've seen in the previous screens, and you'll see the triple bond has the lowest potential energy because the bond length's the shorter. The double bond has the lowest bond energy because it has the longer bond length of the two. Molecular models, we're going to work with this some more. So just a space filling model is more like when you're actually pulling in, when you're making a particulate diagram. And we'll practice this in class. Ball and stick model is what we draw usually when we're drawing 2-dimensional and we're trying to make them look like 3-dimensional. So we'll get to this more in class, but just to show you the differences between the two. All right, so you guys are ready to rock and roll, and I know you're going to do great, and we'll just keep at it. So don't forget, AP Classroom has some awesome videos too. Okay, take care. I'll see you guys later. See you tomorrow. Bye-bye.